All right, let's talk about one of the most ingenious pieces of automotive tech ever invented, the turbocharger. Seriously, this little device completely changed the game for engine performance and efficiency, taking what was once a clever hack and turning it into a true engineering marvel.
So here's the fundamental puzzle that car engineers have been trying to solve for over a century. You want more power. The old way? Just build a bigger engine. Simple, right? But bigger engines mean more weight, worse fuel economy, and they take up a ton of space. So the real question is, how do you get that big engine power out of a small, light, and efficient package? Well, the answer is a brilliant concept called forced induction.
Forced induction is pretty much exactly what it sounds like. Instead of an engine just sucking in air on its own, you use a pump to compress air and literally force feed it into the cylinders. See, an engine needs air and fuel to make a bang. By cramming more air in, you can also add more fuel. And more air plus more fuel equals a much bigger, more powerful bang, pushing that piston down. It is the secret sauce for getting way more horsepower out of the exact same size engine.
Now, there are two main ways to do this. You've got superchargers, which are driven by a belt connected right to the engine. They give you instant power, which is awesome, but they also create what's called a parasitic load. Basically, it takes engine power to make power. But then you have the turbocharger, and this is where it gets really clever. Instead of using a belt, a turbo is powered by something the engine is just throwing away anyway: hot, fast-moving exhaust gas. It's basically free power, and that incredible efficiency is what we're going to focus on.
Okay, so here's our game plan. First, we'll break down what a turbo actually is. Then, we'll take it apart and look at its anatomy. After that, we'll get into the absolutely insane engineering challenges involved. Then, we'll check out the cool, modern tech that solves those problems. And finally, we'll talk about what it all means in the real world, for you and your car.
All right, Section 1, let's get right down to it. What in the world is this little device that can magically spin exhaust fumes into raw horsepower? At its heart, a turbocharger is the ultimate recycling machine. Think about it. All that hot, high-pressure exhaust gas is normally just wasted energy shot out the tailpipe. A turbo captures that energy. It uses the exhaust to spin a little wheel called a turbine. That turbine is connected by a shaft to another wheel, a compressor, which sucks in fresh, cool air, squeezes it down, and shoves it into the engine. It's this beautiful, self-powering loop.
And you might think this is a pretty modern idea, but you'd be wrong. A Swiss engineer named Alfred Bucci patented this concept all the way back in 1905. For decades, it was mostly used in massive engines, especially on airplanes, like the legendary B-17 bomber, helping them fly high where the air is thin. It took until 1962 for this wild aerospace technology to finally make its way from the clouds down to the street in cars like the Oldsmobile Jetfire.
So to really get how a turbo works its magic, we have to pop the hood and look inside. And what you'll find is that it's really a story of two different worlds, a super hot side and a cool side, connected right in the middle. Let's break this down. First, you have the hot side, which is the turbine. This is where the engine's scorching hot exhaust gas does its work. Then you've got the cold side, which is the compressor. Its job is to grab fresh air from the outside, and holding it all together is the center hub, which is basically a shaft with some high-tech bearings that allows both the hot and cold sides to spin together at almost unbelievable speeds. Okay, so let's follow the airflow. Step 1, hot exhaust blasts out of the engine and hits the turbine, spinning it like a pinwheel. Step 2, since they're connected by that shaft, the compressor on the other side starts spinning just as fast. Step 3, the spinning compressor acts like a tiny jet engine, sucking in huge amounts of fresh air and compressing it. And Step 4, that dense, oxygen-rich air gets forced into the engine, making a bigger boom, which in turn creates even more exhaust gas to keep the whole cycle going.
Now, this all sounds amazing in theory, right? Free, recycled power. But making this process work reliably, well, that is a whole other story. It's a true engineering nightmare. We're talking about mind-bending speeds, intense heat, and just incredible physical stress on every single part. And of course, there's that one famous problem everybody talks about: turbo lag.
Ah, turbo lag. It's that classic hesitation. You stomp on the gas pedal and for a second, nothing. Then, bam, the power hits you. That delay is the time it takes for enough exhaust to build up and get that turbine spinning fast enough to actually start compressing air. For decades, getting rid of that lag has been the absolute holy grail for engineers.
Now, take a look at this.
This isn't just some cool graphic. This is what engineers see. It's a stress analysis showing the forces trying to rip a turbine wheel apart. And get this, these things can spin up to 250,000 RPM. That's not a typo. The colors show the stress points, with red being the, uh-oh, this is where it's going to break zone. Engineers use these simulations to design blades that can survive these literally unbelievable forces without just exploding.
And if the speed wasn't scary enough, there's the heat. Exhaust gases can top 1,000 degrees Fahrenheit. We're talking glowing red hot. This simulation here shows how much the metal actually bends and warps under that heat. Even a microscopic change in shape is a disaster. At 250,000 RPM, the tiniest imbalance would cause the whole thing to vibrate itself to pieces. So the material has to be incredibly strong and stable, even when it's literally on fire.
So how in the world do you solve for that kind of speed and heat? The answer is some seriously exotic material science. We're talking about superalloys like Inconel, the kind of stuff you'd normally find in a rocket engine or a nuclear reactor. Using these simulations, engineers can test different materials to find the perfect mix. It has to be light enough to spin up quickly and fight lag, but also strong enough to not melt or tear itself apart. It's a crazy balancing act.
So faced with these massive problems of lag, heat, and stress, did engineers just give up? Of course not. They got smarter. They came up with some incredibly innovative solutions to make turbos more powerful, more efficient, and more responsive than ever before.
One of the cleverest solutions is called a variable geometry turbo, or VGT. The best way to think about it is like having two turbos in one. Inside, it has a set of tiny movable vanes. At low engine speeds, the vanes close up, creating a narrow channel that makes the exhaust gas speed up and hit the turbine hard, which kills lag. Then at high speeds, the vanes open wide to let the engine breathe freely. It's the best of both worlds.
Here's another genius idea, the twin-scroll turbo. Think of the exhaust pulses from an engine like cars trying to merge onto a chaotic one-lane road. They get in each other's way. A twin-scroll design is like adding a second lane to that highway. It separates the exhaust from different cylinders into two separate scrolls, or paths. This keeps the pulses clean and orderly, so they hit the turbine wheel with more focused energy, which makes it spool up way faster.
And now we get to the cutting edge, where things get a little bit futuristic. What if you didn't have to wait for exhaust gas at all? An electric-assisted turbo puts a tiny, powerful electric motor right on the turbo's shaft. The instant you touch the gas pedal, before the exhaust even gets there, that motor spins the compressor up to speed. The result? Turbo lag is just gone. Erased. It's instant power, no waiting.
Okay, we've gone deep on the tech and the theory, but let's bring this all back to the real world. What does this actually mean for you, as someone who might drive, own, or work on one of these cars?
So turbos are built tough, but they're not invincible. And you really want to know the warning signs that one might be in trouble. The big ones are a sudden major loss of power or a strange noise, like a high-pitched siren or a dentist drill coming from under the hood. Also, if you see blue or gray smoke coming out of your exhaust, or if your engine suddenly starts drinking oil like crazy, those are huge red flags.
And here's exactly why you need to pay attention to those signs. That number right there, replacing a turbo is not cheap. You're typically looking at anywhere from $1,500 to $4,000, or even more. Remember all that rocket science material and those insane engineering tolerances we talked about? Yeah, this is what that costs to replace.
So, how do you avoid seeing that scary repair bill? Luckily, it's pretty simple. The number one most important thing is clean oil. You have to do regular oil changes using the high-quality stuff the manufacturer recommends. Oil is the lifeblood of a turbo. It's what cools and lubricates those bearings, spinning at 250,000 RPM. Also, keep your air filter clean. And here's a pro tip. After a hard drive, let the car idle for a minute before you shut it off. This lets the turbo cool down gently and stops oil from cooking and clogging up the inside.
You know, when you step back, the turbocharger is just an incredible testament to human ingenuity. It's a device that literally takes wasted heat and noise and turns it into thrilling performance. It let tiny little engines perform like giants. But as we all start looking toward an electric future, you have to wonder, what will its legacy be? Will the turbo be remembered as the absolute peak of the internal combustion engine, or was it just a brilliant stepping stone on the path to whatever comes next? It's a pretty cool thing to think about. Thanks for joining me.